अगर इस चैनल पे नए हो तो सब्सक्राइब कर देना, और अगर लाइक नहीं किया तो लाइक कर देना। और अगर मेरा रिकॉर्डेड वीडियो देख रहे हो तो चैनल पे जाके मेरा न्यू लाइव स्ट्रीम ज्वाइन कर सकते हो। चलो पहले स्टार्ट करते हैं।
It will keep on becoming more and more weaker. When material keeps on becoming more and more weaker, will it deform more and more or less and less? Though stress is remaining constant, because internally material is becoming more and more weaker, it starts deforming more and more, more and more, more and more. ज़्यादा सा deformation बनते हुए बेटा वो fracture बनते हैं. So in this rapid creep region, softening effect will be more dominant than strain hardening effect. That is the reason why slope of the graph will keep on increasing. Correct? This is how creep will take place. Now, once you have understood this better, moving to another very, very important area, that is, for more creep resistance, for more creep resistance, for more creep resistance, किसी एप्लीकेशन में किसी मटेरियल के साथ अगर आप ज्यादा क्रीप रेजिस्टेंस को एक्सपेक्ट कर रहा है, कौन सा कंडीशंस को सैटिस्फाई करना पड़ता है, ज्यादा क्रीप रेजिस्टेंस पाने के लिए किसी एप्लीकेशन में कौन सा सजेशंस को फॉलो करना है। बेटा सब्जेक्ट की शुरुआत से अलग अलग जगह में मैं क्रीप रेजिस्टेंस के बारे में जो 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 बोलते आ रहा हूं बेटा, वो सारे स्टेटमेंट्स इकट्ठा करके एक ही जगह पे डिक्टेशन का रूप में यहां पर देने वाला हूं। राइट डाउन स्ट्रेट अवे। नंबर वन, यूज मटेरियल्स हैविंग हाई मेल्टिंग पॉइंट टेंपरेचर। use materials having high melting point temperature. Right now, use materials having high melting point temperature. Use materials having high melting point temperature. Number two, use coarse grain structures. Use coarse grain structures instead of fine grain structures. Use coarse grain structures instead of fine grain structures. Number three, dispersion strengthened composites. Dispersion strengthened does not permit permanent deformation easily. That last mechanical test is fatigue test. Right, fatigue test. Right. Friends, you know, whenever we talk about fatigue test, in fatigue test we are trying to examine the behavior of a material that is subjected to fatigue loads. Material behavior under fatigue loads is studied by fatigue test. What do you mean by fatigue loads, sir? A material may be subjected to reverse loading, fluctuating stresses, or completely reversed stresses, or cyclical stresses. Varieties of stresses are there. You must be studying all these profiles of the stress state in machine design. When a material is subjected to fluctuating stresses or repeated stresses or completely reversed stresses, all that material is subjected to fatigue loads. Sir, what happens, sir? When a material is subjected to completely reversed stresses or cyclical stresses or repeated stresses, it is found that the fracture stress of the material subjected to fatigue loads will be very much less than its static ultimate tensile stress. Same material when it is tested in tension test, its ultimate tensile stress is going to be far, far, far higher compared to the fracture stress of the material under fatigue loading conditions. A material which is subjected to fatigue loads will undergo fracture at a value of stress which is much less than its static ultimate tensile stress to the fracture stress of the material under fatigue loading conditions. A material which is subjected to fatigue loads will undergo fracture at a value of of stress which is much less than its static ultimate tensile stress. Now, ये बात साबित करने के लिए बोल दो if the external stress applied on a material is completely reversed, repeated or fluctuated, it will undergo premature failure. बोल के बोलने का जो फैक्ट है, इस फैक्ट को साबित करने के लिए बनाया गया टेस्ट का नाम है fatigue test. Now friends, you can ask me, sir, are there really components that are subjected to this type of stresses? Yes, beta. Rotating shafts, pumps parts, compressor. Parts. Springs, airs, aeroplane wings, these are all components which are subjected to aeroplane wings, pumps parts, compressor parts, springs, tires, aeroplane wings. These are all the components which are subjected to fluctuating stresses, dynamic stresses, completely reversal stresses, cyclical stresses. So in all these components, what is going to be the challenge? Premature failure banta hai. That means these components which are subjected to fatigue loads, they will undergo fracture at a value of stress which is much less than its static ultimate tensile stress. So what is the reason of this reason for this stress? We want to confirm whether it is true that the fracture stress in fatigue loading is less than the static ultimate tensile stress. If it is true, why it is true? Okay, response देने के लिए, reason देने के लिए हम ये वाला टेस्ट कंडक्ट कर रहा है. Now, how do we proceed with this test? Very simple schematic method. Suppose this is, let us say, here I have an electric motor shaft. Suppose this is the electric motor shaft that you are going to see. This is the electric motor shaft. Right? Now, you know, this electric motor shaft can be rotated about its axis. When you put on the electric motor shaft, it starts rotating about its axis. Now, what you do is, through a bearing, try to apply a load on this shaft. Let us say, whatever I am trying to show here is a bearing. Understand? This is a bearing. Through this bearing, we try to apply external stress or external load. Load apply करके रख दो बेटा. Once you apply load divided by area cross section of the shaft gives you stress. Applying load, but load divided by area cross section of the shaft gives you stress. Correct? Next, you try to connect this shaft to what is called as a revolution counter. What is this revolution counter going to do? This revolution counter, let me try to show you here. This revolution counter will keep on recording number of rotations undergone by the shaft. The shaft rotation, number of rotations undergone by the shaft will keep on increasing as a function of time. More the length of time for which you run the motor, more will be the number of rotations undergone by the shaft. And remember, in each rotation, these different layers of the shaft will experience 0 to tensile maximum to compressive minimum to 0. That means in one rotation of the shaft, different layers will experience completely fluctuating stresses. 0 to tensile maximum to compressive minimum to 0, again maximum tensile, maximum minimum compressive, like that. In every revolution of the shaft, each revolution of the shaft must be considered as one complete cycle of fluctuation of stress. Each revolution of the shaft must be considered as one complete cycle of fluctuation of stress. So हम यहाँ पर कौन सा डेटा मॉनिटर कर रहा है? We are trying to apply a stress. Keep the stress applied on the shaft constant. At that constant stress, we keep on running the shaft for any length of time. Maybe 1 million revolutions, 10 million revolutions. चलने दो. Then you wait until this shaft fractures. Now, when the shaft undergoes fracture, after n number of revolutions, find out what is the number of revolutions prior to fracture. Fracture होने तक कितने revolutions से shaft rotate हो गया? Then record the readings. At S1 level of stress, N1 is the number of revolutions before fracture. Now, what you do? एक बार shaft fail हो गया बेटा. Replace it with a new shaft, but out of the same material. Material is same, लेकिन नया वाला component लगाया. Now apply another stress S2 level में. Apply S2 level of stress. Let the shaft run up to fracture. Now find out what is the number of cycles to fracture. Find out that as N2. S1 में S1 stress में N1 number of cycles to fracture. S2 stress में N2 is the number of cycles to fracture. Like that, you will be generating stress versus number of cycles to fracture data. That stress versus number of cycles to fracture data is plotted in the form of graph. That graph is being shown here. That is stress applied on the shaft versus number of cycles to fracture. Number of cycles to fracture. This is called as N. Therefore, fatigue test data is represented in the form of SN curve. It's called as SN curve. Now, when you plot this graph using this stress versus number of cycles data, you are going to get the graph like this. For ferrous materials, like that. For non-ferrous materials, right? So this graph is for ferrous metals and alloys, ferrous metals and alloys, whereas this graph is for non-ferrous metals and alloys. This graph is meant for non-ferrous metals and alloys. Now, what does this graph tell? Also, this graph tells us that if I apply, come on friends, observe this graph and tell me. When I apply a higher level of stress, number of cycles to fracture is less. If I apply a smaller value of stress on the shaft, number of cycles to fracture will be more. When I say number of cycles to fracture will increase, if stress applied is decreased, it means what? Life of the shaft will increase, life of the rotating shaft will increase if I reduce the applied stress. Called as under stressing. What is called under stressing? That means you are applying a value of stress. Number of cycles to fracture will increase if stress applied is decreased. It means what? Life of the shaft will increase, life of the rotating shaft will increase if I reduce the applied stress. This is called as under stressing. What is it? But under stressing means you are applying a value of stress much less than the permissible stress for that shaft material. When you apply a lower level of stress than permissible value, number of cycles to fracture will increase. This is one observation. And this is true not only for ferrous metals and alloys, it is also true for non-ferrous metals and alloys. Let us take another important conclusion. Suppose, come on friends, suppose you apply a level of stress which is below this horizontal line. Did you notice what is happening? For ferrous metals and alloys, SN curve initially decreases, then after a particular level of stress, it becomes parallel to x-axis. Right? When this graph becomes parallel to x-axis, beta, इसका मतलब क्या है? If you apply a value of stress less than this horizontal line, if you apply a level of stress less than or below this horizontal line, what will be the number of cycles to fracture? जब आप ये pink level of line, ये pink line level पे stress apply करते हैं, कितने number of cycles service life मिलेगा तुम्हारे? Infinity. Do you know what is that particular stress known as? Fatigue strength. What is fatigue strength, sir? The highest level of stress. क्या बोला बेटा? Fatigue strength is defined as highest level of stress that can be applied on a material repeatedly. Highest level of stress that can be applied on a material. Highest level of stress that can be applied on material repeatedly. Highest level of stress that can be applied on a material repeatedly for infinite number of cycles. Fracture is called as fatigue length or fatigue, like fatigue strength, not fatigue length. It's called fatigue strength. Now you can define this fatigue strength. Always याद रखो that fatigue strength is defined for infinite number of cycles. The infinite number of cycles of life मिलने के लिए, come on, SN curve should become parallel to x-axis, and that happens only for ferrous metals and alloys. Therefore, fatigue strength is defined. Fatigue strength is defined only for ferrous metals and alloys. सर नॉन फेरस मेटल्स एनालाइज के केस में क्या होता? देखो बेटा आप ही देखो क्या होता, देखो यहां पर इफ यू अप्लाई दिस लेवल ऑफ स्ट्रेस इट विल फेल एट दिस नंबर ऑफ साइकिल्स. इफ यू अप्लाई a smaller level of stress it will fail at this number of cycles. If you apply a lower level of stress there is going to be another definite number of cycles to fracture. That means whatever the smaller level of stress you apply, this graph keeps on declining, telling you that there is only definite number of cycles to fracture. किसी level of stress में आपको नॉन फेरस मेटल्स एनालाइज का केस में इंफिनिटी fatigue life नहीं मिलने वाला है. Because this curve keeps on going, declining, it will this SN curve never becomes parallel to the x-axis for non-ferrous metals and alloys. So किसी applied level of stress पे only definite number of cycles मिलता है तुम्हारे को, infinite number of cycles of service life नहीं मिलता है non-ferrous metals and alloys के केस में. लेकिन ferrous metals and alloys के केस में infinity service fatigue life मिलता है. So SN curve becomes horizontal for ferrous metals and alloys. That is the reason why we are able to define fatigue strength for ferrous metals and alloys. SN curve never becomes parallel to x-axis. Hence, fatigue strength cannot be defined for non-ferrous metals and alloys. तो फिर क्या करना है सर? In place of fatigue strength, we define what is known as endurance strength. Endurance strength is defined for finite number of cycles. Fatigue strength is defined for infinite number of cycles. What is endurance strength? Endurance strength means the highest level of stress that can be applied on a material repeatedly for finite number of cycles. Means the highest level of stress that can be applied on a material repeatedly for finite number of cycles. So what is this finite number of cycles before fracture? 10 power 8. 10 power 8 cycles is generally considered as a good fatigue life. So अगर आप ना किसी नॉन फेरस shaft material से 10 power 8 cycles of loading receive करना चाहते हैं before its replacement, what is the highest level of stress that can be applied? That is called as endurance strength. So endurance strength is defined for non-ferrous metals and alloys. Fatigue strength is defined for ferrous metals and alloys. What? Okay. Now people will ask, right? Why ferrous metals and alloys? The graph is in case of ferrous metals and alloys, the graph is becoming parallel to x-axis, and why it is not becoming parallel to x-axis for non-ferrous metals and alloys? Material science subject element. Why? How? ऐसा वाला क्वेश्चन बहुत ज्यादा रहता है. आंसर करना है यार, दूसरा रास्ता नहीं है. याद में रखो, in ferrous metals and alloys, intercrystalline regions are rigid. Intercrystalline regions बोले तो दो grains के बीच में जो region रहता है बेटा, that region is generally the region which is capable of propagating the cracks easily, because वहाँ पर voids रहता है ना, right? Intercrystalline region is rigid in case of ferrous metals and alloys. Therefore, below a particular level of stress applied, rigid means non-deformable. Below a level of stress applied, हाँ पर कुछ परमानेंट डिफॉर्मेशन बनता ही नहीं. परमानेंट डिफॉर्मेशन ही नहीं बनता है, it will not go to fracture. That is the reason why infinity like यहाँ पर possible हो सकता है. Hence the line becomes parallel to x-axis. In non-ferrous metals and alloys, come on, in non-ferrous metals and alloys, intercrystalline regions are soft. Intercrystalline regions soft होने के वास्ते बेटा, at any level of stress applied, there will be permanent deformation. On ferrous metals and alloys, you apply any level of any lower level of stress, वहाँ पर permanent deformation बनता ही बनता है. जब permanent deformation बनता है बेटा, will it not lead to fracture? जब फ्रैक्चर होने वाला है तुम्हारे को फाइनाइट सर्विस लाइफ मिलता है. तो ये वाला कर्व कभी भी तुम्हारे को इंफिनिटी सर्विस लाइफ नहीं देता है. इट विल नेवर बिकम हॉरिजॉन्टल, इट विल कीप ऑन डिक्लाइनिंग बिकॉज़ इंटरक्रिस्टलाइन रीजंस इन नॉन-फेरस मेटल्स एंड अलॉयज आर सॉफ्ट. राइट बेटा, ये बात सुनने के बाद नेक्स्ट आई एम कंसंट्रेटिंग ऑन अदर एस्पेक्ट. आई एम ट्राइंग टू शो यू हियर व्हाट इज कॉल्ड एज फ्रैक्चर सरफेस अपीयरेंस. ट्राइंग टू शो यू हियर द सो कॉल्ड फ्रैक्चर सरफेस अपीयरेंस. सपोज इन दिस डायग्राम आई एम ट्राइंग टू शो यू a shaft with a keyring. This is the shaft with a keyring that you are seeing here. Like normally, wherever there are geometrical discontinuities, wherever there are surface notches, wherever there are grooves, recesses, notches, these grooves, recesses, notches, keyways, they all become potential sites for creation of crack. Because of stress concentration effects, fatigue crack, initiation, उसी जगह में बनता है. That is the reason why I'm trying to show you here. At this geometrical discontinuity, crack propagation took place in fatigue loading. एक बार जब crack initiation हो गया है, now it has to propagate. How does the crack propagation take place? In the initial stages, under fatigue loading conditions, beta. Under fatigue loading conditions, in the initial stages, what happens is crack propagation will be taking place slowly. When crack propagation takes place slowly, in the shaft cross section, you are going to find this type of beach marks. ऐसा, circular arcs का जैसा जो structure रहता है, this is going to be a smooth surface. This is called as beach marks. These are called as beach marks. These beach marks indicate smooth surface. Beach marks indicate smooth surface. This type of fracture surface will be formed because of slow crack growth. Due to slow crack growth, ऐसा होता है. And due to slow crack growth, fracture surface will be smooth and it will be resulting in beach marks. Now, when the crack propagation, when the crack propagates almost 2/3 of cross section, and due to slow crack growth, fracture surface will be smooth and it will be resulting in beach marks. Now, when the crack propagation, when the crack propagates almost 2/3 of cross section, in the last 1/3 portion of the cross section area, the crack propagates speedily. When the crack propagation takes place speedily, rough surface will be created. So we try to understand here. This rough surface, this is a rough surface, rough region, rough surface or rough region indicates fast crack growth. It indicates fast crack growth. Right. So from this diagram, what you are able to see is this is what is called as fracture surface appearance. Fracture surface appearance is called fracture surface appearance under fatigue loading conditions. Appearance is called fracture surface appearance under fatigue loading conditions. This is called fracture surface appearance in fatigue loading conditions. Up to 2/3 of cross section crack will propagate slowly. It results in smooth surface with the beach marks. In the last 1/3 portion of the cross section, smooth surface with the beach marks. In the last 1/3 portion of the cross section, crack propagation will be taking place speedily. That results into rough surface. Since crack propagation takes place speedily, when final fracture of the component takes place into two pieces, will it be a brittle fracture or ductile fracture? बोलो बेटा. आखिर में in the last, crack is going to propagate speedily. When crack propagates speedily, it results into brittle fracture. Therefore, fatigue fractures are always considered as brittle fractures only. fatigue fractures are always considered as brittle fractures only. Now you can ask me, sir, यहाँ तो slow crack propagation हो गया ना, लेकिन ये वाला fracture नहीं है ना. But a fracture and failure are different. Inability to do intended function is failure. Fracture बोलो तो final separation of the component into two pieces. That is fracture. अब बोलो यहाँ पर final separation of the component into two pieces हो गया क्या? नहीं. Only when in the last portion of the crack propagation takes place, final fracture takes place. तो जब भी लोग बोलते हैं fatigue fractures are always brittle, उनका नजर में क्या है? Final fracture. Is always brittle. So इस रीजन को क्लासिफिकेशन नहीं लेना है. फ्रैक्चर बोले तो जब ये कंपोनेंट दो के जैसा टूट जाते हैं तभी बोलते हैं फ्रैक्चर. So fracture is in this region. In the final fracture stage, crack propagation takes place speedily. That is the reason why. Come on, that is the reason why fatigue fractures are always considered as brittle fractures and sudden fractures. Right. आगे. Sir, one or two more aspects are still there. Under fatigue loading, that is, sometimes experts ask, can you draw a stress strain diagram under fatigue loading? Yes, let us try. Can you draw stress strain diagram under fatigue loading? बोल के पूछते हैं. Let us say this is stress, here is strain. Right? Let me try to show you. In the first cycle of loading, let us say for example, load go applied stress goes from 0 to tensile. Yes, maximum तक जाना है 0 to tensile maximum. Let us say for example, in the first cycle of loading, assume beta, this is yield stress in first cycle of loading in tension, sigma y1 t. 1 means first cycle of loading. Sigma y means yield stress. T means tension. So this is yield stress in first cycle of loading in tension. Come on, go beyond yield stress. Okay, go beyond yield stress. Yield stress के ऊपर जाने के बाद withdraw the applied stress. Applied stress को withdraw कर दिया. Applied stress को withdraw कर दिया. 0 बना दिया. Now reverse the applied stress into compressive region. Apply compressive stress. So when you apply compressive stress, go beyond yield stress again. Suppose this is yield stress in first cycle of loading in compression. What is sigma y1c? Yield stress in first cycle of loading in compression. Again go beyond yield stress. Again go beyond yield stress. Then withdraw the applied stress. Withdraw the applied stress. क्या हो गया बेटे यहाँ पर? 0 to tensile maximum to compressive minimum to 0. This is called as one cycle of loading. This is what happens in one rotation of a shaft. The different layers will go through. Different layers of the shaft will go through this type of stress fluctuation from 0 to tensile maximum, compressive minimum to 0. Right. Normally, all manufacturer design applications will be within the elastic limits. Right. But I am trying to show you this graph in permanent deformation limits because my interest is in metal forming. Normal applications like what I have shown, electric motor shaft, right, compressors, components, pump components, both of them. Normal operation will be within elastic limits, not beyond yield point. But my interest is fracture. Fracture will not take place within the elastic limits. Fracture will take place only when you go beyond yield limits. That's why I am going to beyond yield stress and then withdrawing the extra applied stress to minimum compressive load and then making it 0. Now if you go for second cycle of loading, when you go for second cycle of loading, come on, let me try to show you here. Suppose if you go for second cycle of loading, that is how the graph will come. This is how the graph will come. Right? In the second cycle of loading, graph is higher beta. So let me try to show you. Right? In the second cycle of loading, that is how the graph will proceed. Right? In the second cycle of loading, you will find this point gives you yield stress. This point gives you yield sigma y2t means yield stress in second cycle of loading with tension. Now go beyond yield stress. Again, withdraw the applied stress and reverse the stress applied on the material in the compressive region. Reverse the reload the specimen in the compressive direction. It will go like that. The graph will go like that. Now here in the second cycle of loading, let us say this is yield stress in second cycle of loading in compression. Now go beyond yield stress. Withdraw the applied stress. Right? This is second cycle is completed. Now if you go for third cycle, so what's going to happen? When you go for third cycle of loading, the graph will go like that. The graph will become like that. Now let us say for example, this is yield stress. This point is giving you yield stress sigma y3t, yield stress in third cycle of loading in tension. Go beyond yield stress. Withdraw the applied stress and then reload the specimen in compression. The graph will come like that. The graph will come like that. Now in the third cycle of loading, this is yield stress in third cycle of loading in compression. That is how the graph will go. That is how the graph will go. Right? That means in each cycle of loading, the graph will go like that. Now what is your observation from this graph? Cycle by cycle of loading, yield stress is keeping on decreasing. Come on, यहाँ पर observation करो, यहाँ पर और यहाँ पर. From here, you understand sigma by 3t is less than sigma by 2t is less than sigma by 1t. Right? Sigma by 3t, that means yield stress in third cycle of loading in tension, is less than yield stress in second cycle of loading in tension. It is less than yield stress in first cycle of loading in tension. That means what is happening? Cycle by cycle, as you go from first cycle of loading to second cycle to third cycle to fourth cycle, जब आप जा रहा है बेटा, yield stress of material is continuously decreasing. मालूम है क्या तुम्हारे इस effect को क्या बोलेंगे? When the yield stress of the material decreases cycle by cycle, this effect is known as Boschinger's effect. It is called as Boschinger's effect. It's called as Boschinger's effect. It's called as Boschinger's effect. Write down. One sentence. It's called as effect. It's called as washing just. This decreases cycle by cycle. This effect is known as washing just effect. It is called as washing just effect. It's called as washing just effect. It's called as washing just effect. Write down. One sentence. When a material is subjected to permanent deformation, when a material is subjected to permanent deformation in one direction, then is subject to permanent deformation in one direction, followed by permanent deformation in opposite direction. Followed by permanent deformation in opposite direction. Followed by permanent deformation in opposite direction, comma, the yield stress of the material decreases. The yield stress of the material decreases. Cycle by cycle. The yield stress of the material decreases. Cycle by cycle. Full stop. This is known as washing just effect. This is known as washing just effect. This is known as washing just effect. आइए अब आपसे एक पॉइंट सुनना चाहता हूँ. I have shown this graph only for 3 cycles of loading. बोले तो 3 rotations के लिए मैं दिखाया. If a shaft is going through a billion revolutions, or after a billion revolutions, what will be the yield stress of the material? Very, very low. When the yield stress decreases, what's going to be the consequence? Even at a lower value of stress applied, more permanent deformation will take place. Correct? When yield stress decreases, at a lower value of stress itself, बहुत ज़्यादा permanent deformation होता है. जब बहुत ज़्यादा permanent deformation बनता है, when more permanent deformation takes place, it leads to fracture. तो तब क्या होगा? Fracture stress will become less than its original static ultimate tensile stress. Got the idea? So washing the now, scientist ने क्या किया? He tried to provide a reason. अरे fatigue loading में जो fracture stress होता है, it is much less than the static ultimate tensile stress for the material because cycle by cycle yield stress कम होता जा रहा है. Yield stress कम होने से at a lower level of stress itself, material will undergo more permanent deformation, leading to premature failure. क्या किया? He tried to provide a reason. अरे fatigue loading में जो fracture stress होता है, it is much less than the static ultimate tensile stress for the material because cycle by cycle yield stress कम होता जा रहा है. Yield stress कम होने से at a lower level of stress itself, material will undergo more permanent deformation. Leading to premature failure. क्योंकि इन्होंने रीजन दे दिया. Now coming in, this is what is called the Postal. आइए बेटा. Normally speaking, If you want to understand it further, let me draw another simple diagram here. Let me try to show you here. The diagram that I am now drawing is actually from fracture mechanics. Let me show you here. Suppose the shaft material is subjected to compressive load. It is in a compressive loading condition. Under compressive loading condition इसके अंदर जो slip planes रहता है, those slip planes will extrude like that. Those slip planes will come out like that. Slip planes will come out of this material like that. Under compressive loading conditions, slip planes will come out of the material like that. Right? Now, examine how I am drawing the slip planes. Examine how I am drawing the slip planes. Every slip plane is coming out independently of the other. Every slip plane is coming out independently of the other. तो आइए बेटा, ऐसा स्टेप बाय स्टेप देखने से तुम्हारे को क्या पता मिलता है बेटा? और ये भी अंडरस्टैंड, these are all slip planes. Slip planes inside the material. When a shaft is subject to compressive loading, इसके अंदर रहने वाला सारा slip planes बाहर एक्सट्रूड हो जाएगा. लेकिन कैसे एक्सट्रूड होता? एक के बाद ये. Not all slip planes will come out at the same time. First this fellow will come, next these two planes will come out, then these two planes will come out, then these two planes will come. That means when slip planes come out, this is called a slip band extrusion बोलते हैं. When slip planes are coming out, there will be time lag between slip planes. एक पहले आते हैं, दूसरा बाद में आते हैं. This is all called as time lag. एक के बाद एक बनकर slip planes बाहर निकलते हैं under compressive loading application. Suppose for a moment, within a fraction of time, बेटा क्या हो गया? The stress applied on the shaft has changed to let us say tensile mode. It has changed from compressive mode to tensile mode. The compressive to tensile, tensile to compression. You have observed that. When stress applied on the material changes its tensile nature, these slip bands will be pulled back. Due to atomic bonds, these slip bands will be pulled in. That's called slip band intrusion. अब आइए वापस लौट कर आने में ये सारा slip planes एक ही समय में अंदर आते हैं क्या? नहीं सर, एक के बाद एक ही आते हैं. So there is time lag again in coming back. Right? When some planes have already come back, some planes are just then coming. You understand me? They will be reverting back to their positions slowly, one after the other आता जाएगा. When they are coming slowly, one after the other अंदर आ रहा है. Suppose the external stress applied on the material is again changed from tensile nature to compressive nature. Suppose external stress applied on the material is changed from tensile nature to compressive nature. Again compressive stress applied कर दिया गया. When compressive stress is applied, बोलो क्या होगा? Those slip planes which were earlier coming inside, they will now start moving out. So under compressive loading, these slip planes will move out, slip band extrusions. Under tensile loading effect, these slip bands will come in. That means as the shaft is undergoing rotation, when the shaft is undergoing rotation, in part of the rotation, these slip bands will be coming out. In part of the rotation, they will be going in. They will be coming out, they will be going in. They will be coming out and they will be going in. This is what is called as slip band extrusions and intrusions. बोलते हैं. Slip band extrusions and intrusions. दोस्तों, slip band intrusions and extrusions की वजह से क्या होता है? Let me give you a simple conclusion. Slip bands are going out and coming in, going out and coming in. And when some planes are going out, some planes are coming in due to time lag. Some planes are going out, some planes are coming in because there is time lag between these planes. All the planes are not following the instruction at the same time. Right? There is always time lag between planes. So cycle to cycle, internally coming inside or going outside, coming inside, going outside. In this process, what happens is when some planes are going out, there are some planes that are coming in. वैसे होने में क्या होता है? Dislocations of opposite sign. Remember the interactions between dislocations? Dislocations of opposite sign. Come on. When they come in one line, क्या होता? They attract each other and combine into perfect plane. Yes sir. Dislocations of opposite sign will attract each other and combine into a perfect plane. When dislocations attract each other and combine into perfect plane, number of dislocations will get minimized. Hence the strength of the material will decrease. So due to slip band extrusions and intrusions, opposite type of dislocations will plane, dislocate out or go plane in the instruction at the same time, right? There is always time lag not following the instruction at the same time, right? There is always time lag between planes. So cycles internally coming inside or going outside, coming inside, going outside. In this process, what happens is when some planes are going out, there are some planes that are coming in. Dislocations are opposite sign. Remember the interactions between dislocations? Dislocations are opposite sign. Come on, when they come in one line, they attract each other and combine into perfect plane. Yes, sir. Dislocations of opposite sign will attract each other and combine into a perfect plane. When dislocations attract each other and combine into perfect plane, number of dislocations will get minimized, hence the strength of the material will decrease. So due to slip band extrusions and imperial to each other and combine into a perfect plane, when dislocations attack each other and combine into perfect plane, number of dislocations will get minimized, hence the strength of the material will decrease.
dislocation number 44 medium from dislocation often benefits from making further dislocation more difficult. If dislocation are inherited, this happening effect is reduced and the material might become softer and more prone to particular fatigue strength. All the muscle recording rest specific definition initiation.
So due to slip band extrusions and intrusions, opposite type of dislocations will combine into a perfect plane. The number of dislocations will decrease, hence the strength of the material decreases. ये दूसरा reason है. Will decrease, hence the strength of the material decreases. ये दूसरा रीजन है. स्ट्रेंथ क्यों डिक्रीज होता बोल के बोलेंगे. तीसरा रीजन बोला बेटा. व्हाट इज दैट सर? When these, this stress is changing several number of times. 1 million revolutions बोल तो 1 million cycles of revolutions are 1 million cycles of loading. So stress is changing 1 million times. Stress is changing its nature 1 million times. Okay, every time when you go to second cycle of stress, there is the effect of first cycle. When you go to third cycle, there is the effect of previous cycle, second cycle. When you go to fourth cycle, there is the effect of third cycle. When you go to billion cycle, there is the effect of billion minus one cycle. This is called as back stress effect. This is called a back stress effect. Back stress effect means the effect of previous cycle of loading in the next cycle. That is called a back stress effect. So cycle by cycle, when yield stress is decreasing, what is happening to permanent deformation? At a lower level of stress itself, more permanent deformation will take place. At a lower level of stress, when more permanent deformation takes place, come on, brother. Due to back stress effect, when you go from one cycle to next cycle. Next cycle to subsequent cycle, amount of permanent deformation will keep on increasing. So what is the effect of back stress? The effect of back stress keeps on increasing the permanent deformation cycle by cycle. Number 2, opposite type of edge dislocations will attract each other and they decrease the number of dislocations, hence the strength of the material decreases. If cyclic loading, come on, yield stress of the material decreases cycle by cycle. These are all the reasons for premature failure of materials subjected to fatigue loading. So under fatigue loading conditions, कोई पूछ सकता है बेटा? Under fatigue loading conditions, why does the material undergo premature failure? बोले तो क्या बोलना है? Washing effect एक बोलना, दूसरा slip band extrusions के बारे में बोलना है, तीसरा dislocations will attract each other, number of dislocations will decrease, strength and hardness will decrease बोल के वो बोलते ना, और चौथा बोलना back stress effect increases the permanent deformation, dislocation बोल fatigue loading. So under fatigue loading conditions, कोई पूछ सकता है बेटा? Under fatigue loading conditions, why does the material undergo premature failure? बोले तो क्या बोलना बेटा? Washing effect एक बोलना, दूसरा स्लिप बैंड एक्सट्रूजन इंट्रूजन के बारे में। तीसरा, dislocations come, will attack each other. Number of dislocations will decrease, strength and hardness will decrease, बोलते वो बोल देना। और चौथा बोलना, backstress effect increases the permanent deformation. That's why fracture takes place at premature level of stress level. There is a question in mechanical properties on Bollinger's effect is due to, बोलो बेटा मेरे साथ, Bollinger's effect is due to, क्यों होता है? It is decreasing. Number 1, slip band intrusions and extrusions. Opposite type of ventilations. Number 2, opposite type of ventilation locations will cancel each other. Number of dislocations will decrease, hence strength will decrease. Number 3, backstress effect of previous cycles will keep on increasing the permanent deformation even at lower level of stress. These are all the reasons for immature failure of material like Bollinger's effect. That has completed the chapter on mechanical properties of materials. Alright, now that we have completed the discussion on mechanical properties of material, right, entire chapter is complete. So let me take just a few minutes of time, 5 minutes of time मैं यहाँ पर आज लेना चाहता हूँ। I want to give you the answers for the questions in alloys and phase diagrams from your workbook. Let me write here quickly. You can copy. Answers to workbook questions. Answers to workbook questions. Answers to workbook questions. Right. Topic 2, alloys and phase diagrams. Alloys and phase diagrams. का आंसर यहाँ पर दे दिया जा रहा है. Right, friends. So let me try to give you question by question. I'm giving you question number and answer. Right. Question number 1. Answer is A. Question number 2. D for Delhi. You can copy from the app also, right? Once this is recorded and kept in the app. Question number 3, answer is A. Question number 4, answer is C. Question number 5, answer is C for Calcutta. Next, question number 6. Yeah. Friends, good evening. Let us have the content discussion for today. We are left with very small topics, as today happens to be the closing day of the subject matter on material science. In the beginning, we are going to take the topic on composite materials. In my opinion, it will take nearly 40 minutes of time. We will be able to complete it off safely. And once the composite materials topic is completed, up to there, GATE syllabus will be over. Alright? Then we will be left with 2 more topics. One is corrosion and its prevention, followed by basics of nanomaterials. So as far as these 2 topics are concerned, this corrosion and nanomaterials They are there in the syllabus of only IES examination students, engineering services examination students. Therefore, we'll be taking them up immediately after composite materials. So some of the students, who are exclusively appearing for GATE examination, may please note that I'm going immediately after completing the topic on the composite materials. I'll be sharing the answers of the topic on composite materials from the workbook. Whatever the workbook questions are there, I will be sharing those questions. Remember, composite materials topic is included in the chapter on non-metallic materials. Actually, what has happened is, in the non-metallic materials chapter, we are supposed to take up the discussion on plastics, ceramics, and composites. Right? All the three are supposed to be jumbled together. What exactly has happened is, these plastics and ceramics are, in 2014, the plastics and ceramics are transferred to the other material science part, that is material science general studies part. And the questions which are coming up from ceramics, not even one question is coming up in a year. From plastics, the questions which are coming up are on thermoplastics and thermosets. Those can be answered by the so-called GATE, PLA examination students. Even from the basic schooling-based knowledge, such questions are coming up. In the very recent GATE examination also, we had one such question on thermoplastic materials. The question can be answered right from schooling-based knowledge. Therefore, we don't want to waste your time for want of such brushing up of simple concepts. Right? So we are only going to focus attention on composite materials and complete that. Once the composite materials topic is completed, I'll give you the answers of questions from the workbook from non-metallic materials topic. Next. Regarding corrosion, once the rest of the two topics are completed, like the corrosion and prevention and basics of nanomaterials, complete करने के बाद, immediately my वो topics का workbook questions का भी answers sharing करता हूँ आपसे directly. Second, some of you may be looking for the solutions of the numerical problems, right? Now, what exactly I am planning to do is for spending time with the clients. I thought I would solve all those numerical problems with my own handwriting, and then see that all these solutions of numerical problems, they are uploaded into your app. That much I can do fine. But give me time. All the way up to today, I had the two batches running on, morning and evening, and that's the reason why I could not make the things ready. I could not write the solutions for you. But what I would do is, I would see that the solutions are uploaded by tomorrow evening. So by tomorrow evening, when the solutions are uploaded to your app, the solutions of numerical problems will be available in your app. You can go through the detailed solutions of the numerical problems. And remember, along with formula, with the detailed explanation, everything will be there. And normally, most of the things will follow the same, 99.999% of the things will follow the same thing as I have mentioned. And remember, once or twice, there are always questions in the GATE examination or the IES examinations from out of the syllabus. Especially, once or twice we have come across questions on ceramic composites. So ceramic composites and fracture topics, they are not included either in the syllabus of GATE or in the syllabus of IES examinations. So from outside the syllabus, when the questions have come, normally there will not be any discussion in the class on such things. However, I am going to share the formula with you so that if the same questions get repeated in future, you will be in a position to answer such questions. So with that, let us start the session for today. And I understand, Mr. Girish, you have submitted your question yesterday night. Unfortunately, it did not appear before I left. That's the reason why it could not be answered better. I hope Girish is listening to me now. Girish, I have received a question of yesterday night. That is, transformation of arsenic to martensite completed only at low temperature without retained arsenic. Is it or not? This is what you are asking. Girish, look at the screen. I'm in front of you. Arsenic to martensite transformation has two characteristic temperatures. Number one, martensite formation temperature. Number two, martensite finish temperature. If you are quenching the specimen, only up to room temperature and martensite formation finish temperature is below room temperature, then definitely there will be martensite plus retained arsenic. If martensite formation finish temperature is above room temperature, right, and you are cooling the specimen up to room temperature, the structure will be consisting of only martensite. Martensite formation will be only at low temperatures because martensite formation starting temperature is 210. That means martensite formation will be from 210 below 210 degrees centigrade only, not at higher temperatures. All right, Girish? So, that is the information to you, Mr. Girish. With that information, I am proceeding to the topic on composites. Let us take up this. Composites are always two-phase materials. Composites are always two-phase materials. These two phases are called with different names. We call one phase as matrix phase, and another phase is known as reinforcement phase. One phase is known as the matrix phase, another phase is known as reinforcement phase. Remember, normally matrix phase is a continuous phase, whereas reinforcement phase is a discontinuous phase. Reinforcement phase is a Please continue on space. Now, what is this matrix and what is this reinforcement, sir? While manufacturing of alloys, there will be parent metal as well as alloying element, is it not? Now, similar to the parent metal in alloys, the matrix will be working. Similar to the alloying element, the reinforcement will be working, right? But then what is the difference between alloys and composites? Friends, in case of alloys, between parent metal and alloying element, either there is complete dissolution or there is a chemical reaction between them. But in composites, between matrix and reinforcement materials, there will be no dissolution, there will be no chemical reaction. That is why we are calling these materials as composites. So without dissolution, ये दोनों materials एक दूसरे में डिसॉल्व नहीं होता है. बोले तो अगर डिसॉल्व होता है तो सिंगल फेज बन सकता है. डिसॉल्व जब नहीं हो रहा है, ये दोनों मटेरियल्स जैसा ऐड करके रख दिया गया है कंपोजिट में, वो वैसा ही दोनों फेजेस की जैसा रह पाएगा. Hence, composites are always two-phase materials. There is no chemical reaction between them. That is how matrix material and reinforcement material are selected. No dissolution, no chemical reaction between these materials. Then you can ask me, sir, what is going to be the matrix material and what is going to be the reinforcement material? This is what is the normal doubt. Friends, whether you talk about it as matrix material or reinforcement material, you have to select only from the three basic classifications of materials. The three basic classifications of materials are metals, polymers, and ceramics. Out of these classifications only, you have to select the matrix as well as reinforcement. Now, for example, if you select metal for matrix, the composites are called as metal matrix composites. If you select polymers for matrix material, you call the composite as polymer matrix composite material. If you select ceramics as the matrix material, then you call the composite as ceramic matrix composite material. That means the name of the composite can come based on which material is used for matrix material. Next, number 2. What is the purpose of reinforcement, sir? Always याद में रखिएगा. Reinforcement material is such a material which, when added to the matrix, will improve the properties of the matrix. That means, before you add matrix and reinforcement will have better properties than the matrix material. Therefore, by adding reinforcement into the matrix material, you are going to improve the properties of the matrix material. Then, what is the reinforcement material, sir? To satisfy this condition, reinforcement material can be selected again from the same three materials. For example, suppose you select polymer as the matrix material, right? When one material is already selected as a matrix material, then you are left with two more materials. The two more materials are metals or ceramics. Out of the remaining two materials, any one can be used for reinforcement. As long as reinforcement does not dissolve in the matrix, reinforcement does not chemically react with the matrix, and reinforcement material should have better properties than the matrix material. Next, the reinforcement which is added to matrix material can be in powder form, in which case the composites are called as particulate composites. The reinforcement which is added to a matrix can be in the form of fibers. Fibers means fine thread-like materials. The reinforcement which is added to a matrix can be in the form of fine thread-like materials called as fibers, in which case we call the corresponding composite as fiber reinforced composite. The reinforcement may be in the form of laminate, in which case you call the corresponding composites as laminated composites. Right? So the composites will also be named based on geometry of the reinforcement medium. Accordingly, we have class. Of composites into particulate composites, fiber reinforced composites, and laminated composites. Alright. Now, once you have this clarity, try to understand what can be a composite material. A composite material is a material which is a combination of two materials, matrix and reinforcement. Though you are adding two materials, matrix and reinforcement, these two materials, the properties of these two materials will be transferred to only one, that is called as a composite material. Without any dissolution, without any chemical reaction, the properties of reinforcement will be transferred to proper matrix material. That is the reason why after manufacturing the composite materials, these two phases, matrix and reinforcement, दोनों मिलकर एक ही component का जैसा काम करना शुरू करता है, without dissolution, without chemical reaction between them, then that single component made out of matrix and reinforcement will be called as a composite material. Right. Now, moving forward, based on the geometry of the reinforcement medium, whether it is in the form of powder particles, or it is in the form of fibers, or it is in the form of laminated composites, laminates, we are having three classifications of the composite material. So we write here, composites are classified into three types. They are called as particulate composites. They are called as particulate composites. Particulate composites is first classification. In particulate composites, the reinforcement is in the form of fine powder particles. The second classification is fiber reinforced composites. Fiber reinforced composites. Fiber reinforced composites. And the third classification is what is called as laminated composites. Laminated composites. In case of laminated composites, the reinforcement is in the form of a layer bonded on matrix material. Right? So here there are three classifications of the composite material based on geometry of the reinforcement medium. Come on. Let us try to see these different classifications of the composites in detail. I am proceeding to the first one, that is particulate composites. Particulate composites. Particulate composites. So what is done here? I am writing the principle of these particulate composites. Hard particles of oxides or carbides or nitrides. Hard particles or carbides or oxides are nitrides are dispersed into a soft molten metal. A soft molten metal like aluminum or copper. Like aluminum or copper. Say for example, friends, I show you here a crucible. This is the crucible that is being shown. Into this crucible, let us assume that we are distributing what is called as the powder particles of the oxides or carbides or nitrides, right? Now, let us say for example, into this particular molten metal, we are distributing powder particles of powder particles of oxides or carbides or nitrides. These oxides, carbides or nitrides powder particles, they are called as the reinforcement. And remember always, the melting point temperature of these reinforcement particles, oxides particles or carbide particles or nitrides, the melting point will be far higher than melting point of this molten aluminum. That is the reason why when you mix up the powder particles of oxides or carbides into this molten soft metal, they won't dissolve at all because these powder particles have very high melting point temperature than aluminum melting point or copper melting point. So they don't dissolve, they don't typically react. Now, after thorough churning or stirring, the entire mixture can be poured into your mold, allowed to solidify. After the solidification takes place, it becomes a composite material. Now, from the composite material, if you take a small sample, cut it, and then test it under tension test, you will find that the strength of the particular composite material will be more than that of base metal aluminum or base metal copper. Now, you can ask me, sir, how does strength increase at all? Friends, in a tension test, as you keep on increasing the applied load steadily, beyond yield point, the dislocations in the base metal lattice will start. Suppose base metal is aluminum, dislocations in the aluminum will start moving. When moving dislocations come across the hard carbide or oxide particles, dislocation movement is going to be stopped. When dislocation movement is stopped, slip will be arrested. Resistance to permanent deformation is increased. That is the reason why strength will increase, hardness will increase. When strength increases, hardness increases. Wear resistance will increase because wear resistance directly depends upon hardness. When wear resistance increases, the composites become useful in tool making applications because wear resistance is demanded for manufacturing of tools. In addition, the carbides or oxides or nitride particles that you are adding to molten aluminum or copper, they are having fairly high melting point temperature. That is the reason why materials having high melting point temperature, they are best suited for creep applications. Okay, right? Therefore, these composites, they become best suitable for wear resistance applications and creep resistance applications. So I write here that the advantages will be that strength will increase, hardness will increase by particulate composite manufacturing, wear resistance will increase, wear resistance will increase and creep resistance will increase. Creep resistance will increase. These are the advantages of having what are called as the particulate composites. Now, let us switch over to the next type of composites known as fiber reinforced composites. Fiber reinforced composites. Fiber reinforced composites. So in fiber reinforced composites, as we can see, the reinforcement is in the form of fibers. When I say fiber, I mean fine thread-like material is called as a fiber. Now, say for example, how do you go for selection of fiber materials? Varieties of fiber materials are there. We say aramid fibers, carbon fibers, glass fibers, varieties of materials say fibers manufacturing कर दिया गया है. Now, depending upon the practical application for which you are going to use, fiber material is actually selected. Right? Say for example, in most of the applications, fiber reinforced composites are employed for improving the stiffness. For example, you might have heard about lawn tennis rackets. These lawn tennis rackets, they are made out of fiber reinforced composite materials for better stiffness. Similarly, the tricycles with which small kids in the houses can be trained, those tricycle frames are made out of fiber reinforced composites. Similarly, the रेस कोर्स एप्लीकेशंस में जो बाइसाइकिल्स यूज किया जाता है वो रेस कोर्स बाइसाइकिल्स का फ्रेम्स भी इसी से फाइबर रिइंफोर्स्ड कंपोजिट्स से मैन्युफैक्चर किया जाता है. लाइकवाइज फिशिंग रॉड्स बोल के रहता है, राइट? दोस फिशिंग रॉड्स आर मेड आउट ऑफ फाइबर रिइंफोर्स्ड कंपोजिट्स. हेलीकॉप्टर ब्लेड्स आर मेड आउट ऑफ फाइबर रिइंफोर्स्ड कंपोजिट्स फॉर वांट ऑफ बेटर स्टिफनेस एप्लीकेशंस, फॉर वांट ऑफ बेटर स्टिफनेस एप्लीकेशंस. So youngster modulus fiber material का ज्यादा रहना है compared to youngster modulus of matrix. When youngster modulus is more for the fibers, it means it is having higher stiffness with fiber applications for want of better stiffness applications. So youngster modulus fiber material का ज्यादा रहना है compared to youngster modulus of the matrix. When youngster modulus is more for the fibers, it means it is having higher stiffness. When fiber stiffness is more, you will be able to improve the stiffness of the matrix material. That's the concept. So I write here that fiber material is so selected. Fiber material is so selected that Young's modulus of fibers is much higher than Young's modulus of the matrix, where EF stands for Young's modulus of fibers. Young's modulus of fibers is EF, and EM is Young's modulus. Of the matrix material. Using this rule, fiber material is selected for a given matrix material. Right? Now,
fiber material is so selected that
it pass. Sir, when you are adding fibers to a matrix, the fiber material is so selected that Young's modulus of fibers is always much higher than Young's modulus of the matrix, and there is no chemical reaction, there is no dissolution of fiber material into the matrix material. Satisfying these conditions, when you select the fiber material, it results in increasing the matrix Young's modulus, so that matrix and fiber put together, which is going to be available in the form of a composite material, the composite material stiffness or Young's modulus will increase. Now sir, if अगर ये बात सच है, can we estimate composite Young's modulus? जो material finally ये दोनों से बनने वाला है, matrix और fibers से, but जो material बनने वाला है composite नाम, can we estimate the Young's modulus of the composite material? Answer is yes. So let me write that. Let EC is Young's modulus of the composite material. EC is Young's modulus of the composite material. This Young's modulus of the composite material is estimated by using rule of mixtures. This is estimated by using rule of mixtures. Rule of mixtures. Very soon I am going to show that. Very soon I am going to show that. Now what is exactly going to happen? I'll show you the diagram of a fiber reinforced composite material and then explain. Say for example, this is the diagram of a composite material in which these lines, let us say for example, whatever you are seeing in the form of white colored lines may please be understood. These vertical lines may please be understood as fibers. Vertical lines are indicating fibers, and rest of the material, black colored material, is indicating matrix material. Now in the matrix material, when fiber material is bonded, what's going to happen is, when you apply the external force on this composite material, from the matrix to the fiber, there will be load transfer. From the matrix to the fibers, there will be load transfer. That's number one. So what is the role of fibers in fiber reinforced composites, sir? It will share a part of the load. The load applied on the matrix will be shared partly by the fibers, number one. And number two, why are you keeping the fibers inside the matrix? When you keep the fibers inside the matrix, each fiber, for example, this is fiber, each fiber is surrounded by matrix material. Therefore, the fiber material is not directly exposed to atmospheric attack. That's the reason why from atmosphere, whatever damaging influences are there, like for example corrosion, oxidation type of जो damaging phenomena होता है, so from such damaging phenomena, the fiber material is protected. So matrix will be protecting the fiber material from atmospheric attack or damage, and matrix will be transferring a part of the load to fiber material. That is the reason why the overall performance of the composite will be better than matrix material as such. Is the point clear? Now let us say for example, VF is volume fraction of, VF is called as volume fraction of fibers. VF is volume fraction of fibers. This is in terms of percentage. 30%, 40%. ऐसा रहता है. Right. When I say volume fraction of fibers, I mean it is the ratio of volume of the fibers out of total volume of the compost. Out of total volume of the composite, how much volume is occupied by fibers? That ratio, volume of the fibers divided by total volume of the composite, gives you volume fraction of fibers expressed in terms of percentage. Similarly, we write here, VM is called as volume fraction of matrix material. So similar to what you have heard from me earlier. Define now. Volume fraction of the matrix. is equal to volume occupied by the matrix material divided by total volume of the composite. This is also expressed in terms of percentage. Now, with here, estimation of EC, estimation of Young's modulus of the composite material, estimation of Young's modulus of the composite material. This is what we are proceeding to immediately. So we are proceeding to estimation of Young's modulus of the composite material. We come across two different situations. They are called as case 1 and case 2. Case 1 is known as longitudinal loading. Case 1 is called longitudinal loading. Case 1 is known as longitudinal loading. This longitudinal loading is also known as iso-strain condition of loading. It is also called as iso-strain condition of loading. So I try to show you here that in longitudinal loading, let us suppose this is the composite material. The vertical lines indicate fibers. These are the fibers that are there inside, and the remaining material is the matrix material. What you are seeing here is the total composite material. When this composite material is subjected to external load parallel to the direction of the fibers, when composite material is subject to external load parallel to the direction of fibers, this is called as longitudinal loading. In this particular condition of loading, the strain induced in the matrix material and the fiber material will be same. That's the reason why we call it as iso-strain condition of loading. In the iso-strain condition of loading, Young's modulus of the composite is estimated by the formula EM plus EF into VF. EM plus EF into VF. This is a formula. This formula is what is called as rule of mixtures for longitudinal loading condition for estimation of volume of the composite material. Sorry, I apologize. For estimation of Young's modulus of the composite material, EC. Now, EM is Young's modulus of the matrix, VM is volume fraction of the matrix, EF is Young's modulus of the fibers, and VF is volume fraction of the fibers. So, when you know the right side data, you will be in a position to calculate EC. Always keep it in your mind. Volume fraction of fibers plus volume fraction of matrix put together will be always 100%. Always it's a default function because there are only two items in the total composite. There are fibers and matrix. These two are only making up the composite material. Hence, volume occupied by fibers plus volume occupied by matrix must be always equal to 100% of the total composite volume. Right now. So, always keep it in mind. So, accordingly, suppose in the numerical problem, examiner gives volume fraction of fibers is 40%. You need to understand that volume fraction of the matrix material is the remaining 60%. Right. Now, once you are comfortable with that, we'll take the case 2 for estimation of volume fraction, for estimation of Young's modulus of the composite. Case 2 is called transverse loading. Transverse loading. This transverse loading is also known as iso-stress condition of loading. Iso-stress condition of loading in which the composite material is going to be used. Suppose I try to show you here. This is the composite material. These are the fibers, and rest of the material in the volume is the matrix material. Now, this composite material is subjected to external load in a direction perpendicular to the axis of the fibers. When the external load is perpendicular to axis of the fibers, this type of loading is called as transverse loading condition. In the transverse loading condition, the stress induced in fibers and matrix will be the same. Because stress is always calculated as load divided by normal area. Area normal to the direction of applied load. So, in the direction perpendicular to the applied load, we are taking it here that the area occupied by fibers and matrix is the same. That is the reason why both matrix and fibers are subjected to same stress level. Hence, it is called as iso-stress condition. In iso-stress condition, Young's modulus of the composite is estimated as EM into EF divided by EM into VF plus EF into VM. This is the formula which is used for estimation of Young's modulus of the composite material. Right side is your data here. All this data will be given to you as a part and parcel of the problem itself. Your task is understand the data appropriately and substitute in the formula, then you will be straight away in a position to calculate Young's modulus of the composite material for transverse loading conditions. Sometimes in examinations they ask you what is the ratio of Young's modulus of the composite in the longitudinal direction to that of the transverse direction बोल के तुम्हारे को ये दोनों का रेशियो भी पूछते रहते हैं, वैसा वाला प्रॉब्लम्स भी आपके वर्कबुक में है, राइट. डायरेक्ट फॉर्मेशंस, डायरेक्ट डाटा सब्स्टिट्यूशन, यहाँ पर तुम्हारे कुछ भी कंफ्यूजन बनने की जरूरत नहीं है, राइट. नाउ वंस यू कम टू दिस mathematical formation for estimation of Young's modulus of the composite of fiber reinforced composites, there are certain important notes that we have to write. Let us say important notes for fiber reinforced composites. Note number 1, we write here. Note number 1, the properties of a fiber reinforced composite. The properties of a fiber reinforced composite. The properties of a fiber reinforced composite will depend on properties of a fiber reinforced composite will depend upon a, we write here, the size, shape and distribution of size, shape and distribution of fibers in the matrix. Size, shape and distribution of fibers in the matrix. Next B, we write here the aspect ratio of fibers. The aspect ratio of fibers. When I say aspect ratio means length to diameter ratio of fibers, right? So the aspect ratio of fibers, that is length to diameter ratio of fibers, properties of a composite will depend upon aspect ratio of fibers. And C, the fiber matrix interfacial bond strength, the fiber dash matrix interface bond strength, interface bond strength, interface bond strength. And D, the relative orientation of fibers with respect to the direction of external load, with respect to the direction of external load. Now these are the factors on which the properties of a fiber reinforced composite will depend. Next, we take the note number 2. Now these are the factors for it will. Depend. Next, we take the note number 2. Note number 2, we write here, for a given volume fraction of fibers, comma, a fiber reinforced composite will exhibit superior stiffness. बोलने का मतलब है superior stiffness means higher value of Young's modulus, right? If you exhibit superior stiffness in longitudinal direction of loading, then in transverse loading condition, what is the meaning of this sentence? Most often, this is an important observation based on the mathematical competency of the candidate. Let me tell you here. You know what exactly we are trying to do in this statement? We are trying to compare the youngster modulus of the composite in longitudinal and transverse loading conditions. For example, see here, I have given you two formulae. This is for longitudinal loading and this is for transverse loading conditions. In these two formulae, if you substitute the same data, that is right for EM, EF, VM, VF, in दोनों equations में अगर same data substitute करेंगे, do you know what is going to happen? That in this particular loading, longitudinal loading, you will get higher value of youngster modulus of the composite than in the transverse loading. That is exactly what I have written here in this statement. The second statement is exactly meaning that. Next, let me try to show you yet another important note. Note number 3 is, let L suffix C is known as critical length of fiber. L suffix C is known as critical length of fibers. Right? This is given by, what is the meaning of critical length of fibers? This is also important for you to have clarification on. Critical length of the fibers means, that is, the length of the fibers, the length of fibers are required for, the length of the fibers required for effective strengthening of the composite. Effective strengthening of the composite. Length of the fibers that is required for effective strengthening of the composite material. That is called as critical length of the fiber. This is given by the formula sigma f into d divided by 2 tau b. In this formula, we understand where sigma f is ultimate tensile strength of fibers. Sigma f is ultimate tensile strength of fibers. D is fiber diameter, and tau d is nothing but the fiber matrix interface bond strength. Fiber matrix interface bond strength. Fiber matrix interface bond strength. Now, exactly based on this formulation, there is a question in your workbook. All these three values are given. Substitute those parameters in appropriate units and you will be able to calculate critical length of the fiber. Most of the questions which are asked in GATE examination or in UPSC exam from material science are direct data substitution into the formula. You don't have to derive great many relationships on the spot. But if you have the expression, you will substitute the data and get the final answer. Right. These are the details that we thought we would share with you. Regarding the so-called fiber reinforced composite materials. Now, having seen these details, we are proceeding to the next type of composites known as laminated composites. Laminated composites. Friends, these laminated composites, they are also called as cladded metals or claddings. Laminated composites are also known as cladded metals or claddings. Now, coming in, if you examine the laminated composites, if you see just one diagram, in the laminated composite, the outer layer is what is called as reinforcement, and inner layer is known as matrix. Inner layer is known as the matrix material. Outer layer is called as the reinforcement, inner layer is called as the matrix material. That means you might have seen plywoods, right? Plywood sheets, they are made out of gluing of or bonding of alternate lamellae, right, of the layers. Similarly, here also, one layer of reinforcement is bonded on another layer of the matrix. Outer layer is called as the reinforcement, inner layer is called as the matrix. Reinforcement material must have better properties than the matrix material. Come again. So, how do you bond? When two different materials are bonded together and the two materials start working, after bonding, the two materials start working like only one component, that is called as a composite. And remember, in this process of establishing bonding between reinforcement and matrix material, there is no dissolution, there is no chemical reaction. There is no dissolution, there is no chemical reaction. How are you going to achieve, sir? There is what is called as explosive bonding. You will be normally calling it as explosive welding technique. That's one technique. Extrusion, suna hoga aapne, hot extrusion, another technique. Similarly, hot roll bonding must have been heard by you, right? Hot rolling. So hot rolling, extrusion, and explosive bonding are the techniques which are normally employed to produce this type of composite materials. Now, Did you observe? In the earlier cases of particulate composites and fiber reinforced composites, the reinforcement went into the volume of matrix material. Therefore, by particulate composites and fiber reinforced composites, internal volume properties will be improved. But here, the reinforcement is there only on the outer surface of the matrix material. Therefore, the internal volume properties of the matrix will not be modified. So, by laminated composites, since there is reinforcement only on the outer surface, only surface properties of the matrix will be improved. Those are the objectives. So, we write here, objectives of laminated composites are to improve surface properties. To improve surface properties. Come again. Sir, how do you bond when two reinforcement and matrix material? There is no dissolution, there is no chemical reaction. There is no dissolution, there is no chemical reaction. There is what is called as explosive bonding. You will be normally calling it as.
Welcome to the stream. Subscribe.
Explosive welding technique. That's one technique. Extrusion. सुना होगा आपने? Hot extrusion. That's one technique. Extrusion. सुना होगा? There is what is called as explosive bonding. You will be normally calling it as explosive welding technique. One technique. Extrusion. सुना होगा आपने? Hot extrusion. Another technique. Similarly, hot roll bonding must have been heard. Right? Hot rolling. So hot rolling, extrusion, and explosive bonding are the techniques which are normally employed to produce this type of composite materials. Now, did you observe? In the earlier cases of particulate composites and fiber reinforced composites, the reinforcement went into the volume of matrix material. Therefore, by particulate composites and fiber reinforced composites, internal volume properties will be improved. But here, the reinforcement is there only on the outer surface of the matrix material. Therefore, the internal volume properties of the matrix will not be modified. So, by laminated composites, since there is reinforcement only on the outer surface, only surface properties of the matrix will be improved. Those are the objectives. So, we write here, objectives of laminated composites are to improve surface properties, such as, I am writing here, corrosion resistance and wear resistance, and wear resistance, corrosion resistance and wear resistance. These are the surface properties. They will be modified or improved by laminated composites. Next one, we write fatigue resistance and creep resistance can be improved. Fatigue resistance and creep resistance. Fatigue resistance and creep resistance can be improved. Similarly, electrical properties and magnetic properties. Electrical and magnetic properties are also surface properties. Electrical and magnetic properties of surfaces can be improved. And then another objective is there, that is to improve uniformity of heat distribution. To improve uniformity of heat distribution. To improve uniformity of heat distribution in different applications. Wherever you would like to achieve uniformity of heat distribution, laminated composites are employed. Alright. Now let us say, for example, we'll try to write certain examples of laminated composites are. Examples of laminated composites are, number one, let's say for example, alclad. Alclad means this indicates high purity aluminum layer. A high purity aluminum layer bonded to a commercial purity aluminum layer. A commercial purity aluminum layer. Alclad means outer layer is aluminum, inner layer is also aluminum. But outer layer is high purity aluminum, inner layer is commercial purity aluminum. So what is the purpose of this? If you examine this alclad composite, the purpose of this composite material is, I write here, this is used for lightweight and good corrosion resistance. Used for lightweight and good corrosion resistance. Good corrosion resistance in aerospace applications. Good corrosion resistance in aerospace applications. That is one example. Similarly, we can write the example set number 2 called as copper clad steel. As I write copper clad steel, you can see this copper clad steel composite even in your house. In the kitchen, there are copper bottom stainless steel vessels that are being employed. Right? Copper bottom stainless steel vessels are what I have written here as composite material. They indicate that outer layer is copper, inner layer is the steel. They are used to improve uniformity of heat distribution. They are used to improve uniformity of heat distribution in cooking applications. In cooking. Similarly, we write copper clad aluminium. Copper clad aluminium means outer layer is copper, inner layer is aluminium. And you know, copper melting point temperature is 1083 degrees centigrade. More than that of aluminium. Aluminium melting point is around 660 degrees centigrade. So outer layer is having higher melting point than inner layer. That is the reason why creep resistance of the composite material will be improved. So we write here, this is used to improve creep resistance of aluminium. To improve creep resistance of aluminium. This is used to improve creep resistance of aluminium. Right, friends? That is the scope of coverage. That is the scope of coverage of the content in the so-called composite materials and in non-metallic materials. In the topic number 3 on non-metallic materials, whatever plastics and the ceramics part is there, that's going to be covered in material science general studies part in the online training program. You can listen only then. Right. With that, the gate syllabus is completed. So what exactly we are part in the online training program? You can listen. Whatever plastics and the ceramics part is there, that's going to be covered in material science general studies part in the online training program. You can listen only then. Right. With that, the gate syllabus is completed. So what exactly we are trying to do is, we are now trying to give you the answers for workbook questions. Answers for workbook questions. So number and answer is A. Question number 8, answer is A. Question, solutions to numerical problems. That is going to be uploaded into the app. Right. Information. And those of you who are on your completed. Now, rest of the 2 topics that I am going to deal with are the corrosion and basics of nanomaterials. And today again, we will be going for dinner at about 8:20. So take it in your mind. Please register this information. And those of you who are probably leaving the training program right now because they may be looking for only gate coaching, please note that from tomorrow 6 p.m. onwards, another subject, machine tools, is going to start, right? Mission tool subject is going to start from tomorrow, 6 p.m. onwards, right? Next, friends, let me take up another topic. Corrosion. This is only for IES students. Corrosion and basics of nanomaterials, they are the topics which you can answer even from your schooling level of knowledge. Again, even if I speak from here, same information will be reviewed. Now friends, there are two basic types of questions as far as corrosion is concerned, only for IES students. Come again. First question is, what is corrosion? Why corrosion is considered as a serious problem in the industry? Right, this is first question. What is corrosion? Why corrosion is considered as a serious problem in the industry? Second question is, what are the different types of corrosion? How do they manifest? How to prevent them? Now, by the time you cover these things, the syllabus content in corrosion will be complicated. Come on, friends. First question. What is corrosion? Why corrosion is considered as a dangerous problem in the industry? Right. Some of the GATE students, those of you who are probably leaving the training program today, please note my email ID. In future, if you want to have any clarifications in material science, you can use it. Right? My institute at gmail.com. Right? Material science medicine at gmail.science, you can use it. Right? My mail ID is very simple. Material science, my subject. Medicine, my institute at gmail.com. Right? Material science medicine at gmail.com. Material science medicine at gmail.com. Go with you until you settle in your career. All right, friends. Design engineering applications, they are not present in pure metallic form. They are present as their ores. Oxides, carbonates, aluminates, sulfides. Now, if you question why most of the metals are existing in the form of their ores, लेकिन pure metallic form में क्यों नहीं हो रहा exist करते हैं? बोलते बेटा, answer is simple. Ore form of existence is going to give it highest stability. So ore form of existence is the lowest energy state, which gives it stability. Ore form of existence is the lowest energy state, and that gives the material highest stability. That is why most of the metals that we need in our engineering practice, they are present in earth crust in the form of their ores. All right. There is a small group of other metals called as noble metals, like gold, silver, platinum का जैसा. ये क्या करता है बेटा? They are called as noble metals because they exist in earth crust in their original form. Now, if you ask why, sir, why like that? Because their original form is the lowest energy state giving form for those metals. That is the reason why gold, silver, platinum type of metals, they exist in earth crust in their original form, but they are very few. They are called as noble metals. On the other side, majority of the metals that you need for design engineering applications, they exist in earth crust in the form of their ores. लेकिन हम ores को लाके सीधा engineering applications में use नहीं कर सकते हैं. Why not, sir? Whatever properties are demanded in design engineering applications, they will not be satisfied by ores. Therefore, ores को सीधा ले आके हम engineering applications में इस्तेमाल नहीं कर सकते हैं. तो फिर क्या करना है? We have to first convert the ores into pure metals. Then those pure metals must be converted to alloy form. Then you have to use alloys for design engineering applications. Now, this process of converting ores into pure metals is called as extraction. Right? The process of converting ores into pure metals is called as extraction process. But you know what is going to happen in extraction process? What is that we are going to do? A lot of energy is input. In extraction process, a lot of energy is input, so that the ores are removed from pure metals and pure metals are extracted. But you know, energy can neither be created nor be destroyed. The energy input into the extraction process is through chemical reactions. Now, through chemical reactions, you are inputting a lot of energy, right, into the extraction process. Using this energy, the ores will be separated out from pure metals. So, by extraction process, you will be able to get the pure metals. But remember, since energy can neither be destroyed nor be created, whatever the energy you have input, that energy will be absorbed by the pure metal. Therefore, by extraction process, you will be getting the pure metals, but they reach high energy state. Pure metals will be in a high energy state, which is unstable state. So, by using extractive metallurgy techniques, when you convert ores into pure metals, you will be able to get pure metals, but they are in a high energy state and unstable state. Since they are in an unstable state, these pure metals will be trying to interact with atmospheric factors. एटमॉस्फेयर में रहने वाला जो इलेक्ट्रोकेमिकल फैक्टर्स, इलेक्ट्रिकल फैक्टर्स, बायोलॉजिकल फैक्टर्स बोल के रहता है बेटा. The pure metals will be in contact with biological, biochemical, electrochemical factors in the environment, and उनका सहायता लेके pure metals दोबारा और फॉर्म में कन्वर्ट हो जाते हैं. क्यों सर? अनस्टेबल फॉर्म से स्टेबल फॉर्म तक चले जाने के लिए. So we use technology. We use technology to convert the ores into pure metals. We use technology, but pure metals, they depend on naturally available factors in the climate and the atmosphere. and they, taking help of atmospheric factors, they again get converted back into ore form. When pure metals get converted back into ore form, this process is called as corrosion. Right? So what is corrosion? Corrosion is a process whereby pure metals get converted back into the form of their ores. Why? In order to go from unstable state to stable state. This is what is going to happen. अनस्टेबल स्टेट से स्टेबिलिटी पाने के लिए प्योर मेटालिक मटेरियल्स एटमॉस्फेरिक फैक्टर्स का सहायता लेके ओर फॉर्म में चले जाते हैं. दिस प्रोसेस ऑफ प्योर मेटल्स गेटिंग कन्वर्टेड टू द ओर फॉर्म इज कॉल्ड एज करोशन. ऑलराइट सर. सो करोशन से क्या होता है? बाय विद करोशन स्टेबिलिटी विल बी ऑब्टेन्ड. विद करोशन स्टेबिलिटी इज गोइंग टू बी ऑब्टेन्ड. ऑलराइट. ये तो अच्छा ही है ना. देन व्हाई डू यू से दैट इज अ प्रॉब्लम? यस, इन द प्रोसेस ऑफ करोशन मेटल possesses all its useful properties and develops useless properties. That is why corrosion is considered as a problem in the industry. What do you mean by that, sir? By corrosion process, yield strength of the material decreases, ductility, useful properties, and depth obtained. All right. ये तो अच्छा ही है ना? Then why do you say that it's a problem? Yes. In the process of corrosion, metal loses all its youth. Full properties. It develops useless properties. That is why corrosion is considered as a problem in the industry. What do you mean by that, sir? By corrosion process, Yield strength of the material decreases. Ductility. Material decreases. Conductivity. Metal decreases. Brittleness increases. Resistivity increases. That means useful properties will damage and useless properties will increase. This is the reason why industry considers corrosion as a serious problem.
चलो बाय बाय। अभी खाना खाने जाते हैं, फिर दोपहर में फिर से आएंगे लाइव।